Hey everybody and welcome. In this video I am going to talk about elementary algebra. And this is the basic algebra that you learn, at least in the United States, as part of the curriculum partly in grade school and then definitely in high school. Now I know, at least for me, it was clunky and kind of boring to learn, but at least the way it was taught throughout high school. And so I'm making a video on elementary algebra in a way to hopefully make it more exciting than maybe you originally thought it was. And to start it off, I want to talk about the history of algebra, because it took over 2 millennia to build the system and form that we use today. And it can actually be segmented into 3 different notational eras. So the symbols and communication that was used to describe mathematical knowledge. And so we have the first one, which was rhetorical algebra, which would be like, they would write something like 1 plus another 1 is 2 things. And so you could imagine how clunky and slow even this would be to write all mathematical knowledge for that time period. And this actually dominated the landscape from ancient Babylonians all the way until the 16th century. So for the bulk of mathematical history, we were using rhetorical algebra written in this form. Then came along Diophantus, and obviously there's a lot of figures, people, societies that contributed to mathematical knowledge, but I'm really just going over the biggest and most eventful pieces of work throughout time and throughout history. And Diophantus was one of them, who gave us our syncopated algebra, where it was a combination of this rhetorical algebra I just wrote up here and some symbolism, so some symbolic nature to represent figures, numbers, objects. And we can credit him with a lot of that work. And then came along Al-Khwarizmi, I believe it's pronounced. I probably butchered that, to be honest. And he came along and gave us a much more symbolic nature to algebra. But again, it's still syncopated, but he is often credited as the father of algebra, the way he was able to solve higher degree polynomials. And so you can dive into the history. Using The History of Mathematics by Boyer is the book I recommend. I think the last edition was written in 1991, but this goes into all the different people, places, and just all of the different historical accounts of mathematics. And now we have symbolic algebra, which is credited to Descartes, and Descartes gave us the frequently used variable x and how we use that in equations. And then obviously you can use y and z, and even the Greek alphabet is frequently used, like theta and pi, right? All the different Greek letters you can use. And then I also wanted to break up the 4 conceptual stages, so the 4 ideas that were prevalent in the history of mathematics. And obviously we started off with just doing plain geometry. We didn't go straight to algebra first. We did plain geometry, which is just understanding shapes and their relationship with each of their sides and angles and their relationship with other shapes. And this was plain geometry. But then eventually we finally did start to move to static equation solving, which used probably rhetorical and syncopated algebra to perform. And then came along Leibniz and Newton in the 17th century, and we got the dynamic functional stage of mathematics, where now we had multiple inputs that described some output, and it was a dynamic change to the way they were doing mathematics. And finally developed in the 19th and 20th century, and what we are currently working on now and using is abstract algebra, where we no longer think about physical quantities, but purely our abstraction of math. We are thinking purely in ideas. No longer do we apply physical quantities like we did in the dynamical function stage. And that's just a brief history of elementary algebra. And with that, we can move into how I'm going to break it up. Okay, and those 5 areas are variables, terms, equations, simplification, and system of equations. And I'll quickly run through each one. Now, variables are exactly what they sound like. It is a variable that you've probably been exposed to before, and variables are symbols that we use to represent a quantity that is changing, that can change, and is flexible. And it can be broken up into dependent or independent variables, and they're almost always represented by letters, either in the alphabet or in the Greek alphabet. For example, x typically represents a independent variable. Not always, but typically will represent an independent. And then y, for example, could represent the dependent variable. And all this means is y depends on whatever the input for x is. So x is an input, y is an output. And it can be any numerical value, any number we want, we could plug in for x, and then we will get a subsequent y for that input. Or we might not get any output because there is no solution given that input. And that is variables. Now we can extend this even further, and we can get terms. Terms are when you add or subtract 2 different quantities, 2 different variables, or the something similar. For example, 2x squared is a term. This is a term right here. We have a constant up front, and we have a variable raised to the second power. This is a term. We could add another term. Let's say just x. This is 2 terms, and 2 terms equal an expression. Any number of terms is an expression. We have the first term and we have the second term. And this leads us to the equations. Equations use 2x squared. We have an expression that equals another different expression. Let's say y. There we go. 2x squared plus x equals y. So this expression equals this expression, and we have an equation. And this leads us to another one. We could even go to 2x squared plus x is greater than or equal to y. And now we have an inequality. And obviously there are infinitely many variations of expressions and terms to get equations and inequalities, but practicing these is how you best learn them. But intuitively and conceptually, these are the first 3 areas you would learn in elementary algebra. Now that we have those 3, we can move to simplifying an equation or an inequality or even just an expression. We can simplify things so we can manipulate them to make sense of them for the physical world that we are looking at or studying. For example, we can simplify x squared plus 6x plus 5. We could simplify this quadratic by factoring it. And we would get x plus 5, x plus 1. And these actually, I wrote an arrow, but these are equal to each other. They mean the same thing, because if we use the distributive property between these 2 terms, we would get this expression. And so This can be useful when we are trying to analyze an equation, an inequality, a system of equations, functions, and so on and so forth. This ability to simplify is useful. Which brings us to system of equations. And for this, I will actually do a complex example that uses a real-world application. And we will see that here in a second. But before I do that, I forgot, with equations, we actually have multiple types of equations. For example, this was a quadratic, a very specific type of polynomial. And a monomial would be just one term. And a binomial will be two terms. And a trinomial will be three terms. And any expression that has two or more terms is a polynomial. So, that's just an example. Also, equations can be either linear or nonlinear. For example, all of these equations or expressions are nonlinear because when they are graphed, they show some sort of curvature structure. If there is no term raised to a degree higher than 1, we will have a linear equation, a linear expression, because it will produce a straight line. All right, and now we can work on this system of equation application problem, and I want to use a biology topic. And so imagine we are dealing with linear growth models. And let's say the subject is insect growth. So insects. And we're talking about larvae. And so we have two models. Let's say the first model is written as, y minus 8 equals 1/12 t. And so when we have variables, we should always say what those variables are. And in this case, the variable t equals time. And time is in hours. And then y is going to be, we're talking about insect growth, so we can use mass in grams of the larvae. And so we have this first model here of insect A. And then we have another model. We have insect B. And this model is y equals, let's say, it's 25. Sorry, that was kind of hard to read. 25 over 12 t plus 1. This is the model for insect B, and this is the model for insect A. And so we have two models here, and this creates a system of equations. We have a system of equations. And they use the same variables, so no confusion there. And when we have a system of equations, we can apply two methods, one of two methods. And then in this case, we will apply the substitution method. And the other option is, of course, the elimination method. And you'll learn that in algebra, this is not a comprehensive lecture. There are many, many theorems, methods, techniques for performing algebraic properties. The purpose of my video is to get the intuitive understanding of the concept or the branch of elementary algebra. And so that's what we are doing with this system of equations problem and everything else I've already gone through in the video. So now we can apply the substitution method. Let's give ourselves some room here. We have the substitution method. And with it, we plug in our y. So we have a model saying y equals something, and we have a model that doesn't have a y equals something. So we can plug in this. We can plug this in to the y in the other equation into here. And that's the substitution method, because y equals this, and y is right here. So we can plug this guy into y. And so let's do that. So we get 25 over 12t plus 1 equals, whoops, not equals, minus 8 equals 1 over 12t. And now we have a single variable, so we can solve for that variable t, which is time in hours. And so to do that, we just perform some basic algebra. We have 25 over 12t minus 7 equals 1 over 12t. We can then add that 7 to this side. So we get 25 over 12t equals 1 over 12t plus 7. We can then subtract 112t from both sides to get 2t equal to 7. We can divide by 2 on both sides, and we get t is equal to 7 over 2. And this is also equal to roughly 3.5 hours. So what is the interpretation of this 3.5 hours that we solve for? Well, what it tells us is that, and this is what system of equations is for, is finding a point of intersect. And I'll show you the graph at the end here. But before we do that, at the time 3.5 hours, both insect A and insect B will have the same mass. I'll say it again. At 3.5 hours, both insect A and insect B will have the same mass. And so what is that mass? Well, we can plug our 3.5 hours into t for both equations and see that they both are the same. And so we need room once again. Let's go ahead and do that. So let's use a different color. Let's use this color. And so we're going to plug in 7 over 2 for both equations. So we are trying to identify what y is when t is 3.5 hours. So my mistake there. So what we can do is this one's already in y equals form, so we can use that pretty easily. So insect B is y equals 25 over 12 times 7 over 2 plus 1. And so if we solve for this, y equals, let me plug it into the calculator. Whoops. We get y is equal to 8.29 and a few more digits, but we'll round it there. So we get 8.29 grams. Y is equal to 8.29 grams. And so to verify that we are correct with our substitution method, we now plug it into the insect A. And we have to rearrange insect A. Right now it is at, let's use another color, y minus 8 equals 1 over 12t. Add 8, y equals 1 over 12t plus 8. So then we plug in our 3.5 hours, and we get y is equal to 1 over 12 times 7 over 2 plus 8. And if we plug that into the calculator, 112 times 7 over 2 plus 8, we get equal to 8.29 grams. And so we can see that these two are in fact the same at time t, which is 3.5 hours. At 3.5 hours, both insect A and insect B will be 8.29 grams. And so you can see that this is useful. Imagine you are observing, you're a scientist and you're observing insect A, or perhaps you observed insect B, and insect A was already a model published online, which you can actually find here at biology.arizona.edu, where they did a hypothetical model and gave me y minus 8 equals 1 over 12t. And then you went in the lab and you observed your own larvae, and you constructed this model, this linear model of y equals 25 over 12t plus 1. And you could actually bound this, right? You could say that this model is only applicable from, let's say 0 times 0 to time 48 hours. So this linear model only applies between 0 and 48 hours. After that, it turns into an exponential model, or a nonlinear one, for example. And you can see that your insect behaves and grows differently than insect A. In fact, insect B grows much faster than insect A. And you can use critical thinking and your analysis skills to determine why that is, what's the importance of that. Let's say it's not insect larvae. Let's say you're dealing with pharmaceuticals or drugs. Anything in the life sciences can be fascinating and useful. And so I said I would use a visual representation or a graph of our models and our system of equations. And so here you go. And we can see quite clearly that at 3.5 hours, it doesn't have units on here, but at 3.5 hours, these two models, their linear curves, their lines, are intersecting at 8.29, which is the mass in our situation. And you can see that this second equation, which is the one that grows much faster than the first one, and you can see that visually here with this blue line, it's growing and growing much faster than insect A, which is this red line. And so there's your graphical representation. You can see a system of equations tell us the point of intersect, if there even is one. Sometimes there won't be one. Sometimes they run parallel to each other for all real numbers, or they intersect multiple times. This would require a nonlinear model. And so you have multiple points of intersect here. Again, this is not a comprehensive lecture or video. This was to gain an intuitive insight into elementary algebra. There are many, many theorems and techniques and models and methods you can learn. And the only way to learn it, or the best way to learn it, is practicing it. But I think this is also extremely useful to start out, is to get an entire big picture overview of a given domain of mathematics, such as elementary algebra. And with that, we will see you in the next video.